Okay, so our approach here. The things we've already done is we've already done a literature search because we did that when we were writing the proposals. We've already downloaded the images and catalogs. Now, maybe you haven't, I have. Certainly by the end of this week, I want you to be capable of downloading the images and the catalogs yourself. But in the context of this stuff, I've done that for you. I've also band merged the catalogs together. We discussed band merging earlier. So our tasks, our big, broad tasks, are going to be to define the region that we care about for the nebula stream and settle on what we want for that sample. We need to learn how to make and interpret SEDs. I want to teach you how to do image inspection when you're looking at the images with the SEDs. I want to help you learn how to make and interpret color, and color magnitude diagrams. And then we're going to try to synthesize the results that we have so far and connect them to the bigger picture, but we're not going to be able to be completely done with this project, even just one of the goals, I think, by the end of this week. I think there's going to be still plenty of work for you to do after this week. So in practice, it's not a linear process. In practice, it's going to be really circular. It's not going to be at all linear because we're going to define what we think the nebular stream should be. We're going to do image inspection, SED creation, CMD creation, and we're going to do all these things together. And then we may decide we want a different sample, and so we'll have to do it all again. And floating over all of this is the fact that the catalog probably has flaws in it, right? I mean, I did the best that I could merging things, but I don't know exactly the properties of the catwise and unwise catalogs. I don't know exactly how good they are. I don't know where the pitfalls are. Certainly, I've tried to do things that work, but you may very well find that there are two sources listed. There's a single source that's listed as two sources in the catalog that really should just be one source. So it's going to happen, and you're going to have to work along the process of debugging the catalog as well. So when we do this live and in person, I'm going to ask you to think about why there are some reasons that we would do these three broad tasks, and why does it have to be circular or recursive, and why sample selection matters. Here are some examples of image inspection. So one of the things that we're looking to find out is if it's a real source or an artifact. So in that first image here, you can barely see there's a circle. The circle is centered on a source that we know is there from another band. But look at that weird modeling that's sort of in a stripe left and right. That's an artifact from a bright star. And so unless you knew for a fact that there was a star there, you probably wouldn't believe that there was a star there. So the photometry measured from this image for that object is not going to be hot because of all those artifacts. Is the source significantly non-circular? Here we have an example where there's two sources. You can see the bright one here, but then you can sort of see there's an appendage off the edge, and the appendage is a separate source. So this is an example of a source that's significantly not circular because there's actually two sources there. There are going to be plenty of examples of places where we can see the source in the image, but we might not have the photometry. I think this is going to happen most commonly with IRAC, because in the nebular stream, there's not been lots of work done in this, and there's lots of nebulosity that can confuse the pipelines. So it's entirely possible that in the process of image inspection, you'll come up with a short list of sources that you can see in the IRAC images, but we don't have any measured photometry for it. And so we'll have to do that photometry. Another thing we need to look for is whether or not the source is matched correctly across bands. So here we've got an example of a source that's next to a bright source. And so depending on what search radius you used, this faint source may have gotten some of the photometry that goes with the bright source. And over here, we've got a really faint source next to a brighter source. And so that's a more obvious situation because the sources are closer and this one is much fainter. It's entirely possible that the catalog will end up, taking the photometry from this guy rather than that fainter one. One of the things that we're going to have to worry about is whether or not the source is really detected at any wavelength longer than WISE-3 or 12 microns. Because we do have clumps of ISM here, it is going to matter. So here's an example, not from IC417, but it's still, the essence of it is still what I think we're going to find in IC417. So here we've got a bright source. It's clearly there, it's clearly bright, and it's triangular because that's the shape of the IRAC PSF. So there's a clearly bright source IRAC1 and IRAC2. Now, IRAC3, there's some interesting things going on. There's this apparent source here, but that source doesn't appear in any other bands. That turns out to be an artifact because this source is so bright. That was where on the chip the source was in the prior exposure. So that's an artifact. That's not a real source. And if you look, you can see that there's sort of structure coming off. That's nebulosity. And when you look in IRAC4, you can see the nebulosity is even brighter. And then when we look in MIPS24, the source seems extended along the lines of along the same direction of where the ISM is. So the photometry that we're measuring, maybe at IRAC4, but certainly by MIPS24, is being substantially affected by the interstellar medium. So I didn't go through, because I haven't done the analysis for IC417. I don't know for sure that we're going to see this. We don't have IRAC3 or 4 or MIPS24. But because we do have nebulosity, I'm pretty confident we're going to find sources like this where the longer wavelengths are affected by the interstellar medium. And another possibility is going to be that there's more than one source at shorter bands that at the longer bands get merged into one. So that's going to matter too. That's why we do the image inspection. And then the SED inspection. So one of the easiest things to note is the SED smooth or discontinuous? So here's 4 examples. And these, I think, are actually from IC417, because you see in the top left, there's a position-based name, but in the top right, it says JOS 17. So this is probably in our catalog because it appeared as a YSO candidate in JOS 17. Look at this. We've got a nice SED down here and this weird outlier. That is not physical. So there's something wrong with that one point. That one point is not right. So we need to investigate why that one point is there. And does it arise from a source mismatch or not? The fact that we've got other cyan diamonds suggests to me that it's just that one point that's off, not the whole source. That's in contrast with this guy. So here we have a nice shaped SED. There's a couple of cyan triangles that are from the same survey. The cyan triangles, I think, are pan-stars. And you see that some of the cyan triangles are right where they should be, and there's one off. It's not as off as this one, but it's still off. So again, I think it's just the one point that's off. But here we've got both of the red diamonds are off. The red diamonds are a different near-infrared. The black diamonds are 2-mass. And since all of the red points are off, I bet it's grabbed the wrong source for the match from that catalog, the catalog that's represented by the red diamonds. So here we have something where we've got a relatively nice SED down here, but then this up here. So here's an example where all of the cyan points are off compared to the rest. So I bet the wrong source was grabbed from the cyan survey. And then here we've got some that seems to be missing some photometry, or there seems to be a lot of variability. Because look, the 2 circles are both IRAC data. The black is from Glimpse and the yellow is from JOS. And you can see IRAC1 for the both measurements are pretty close, but IRAC2 is much different. Now, these people are working from the same data. So the fact that it's substantially different does not mean that it's variable because they're working from the same data. So something's wrong with one of those sets of photometry, or it's grabbed the wrong source. So these are the kinds of things you're going to need to look for the SED inspection. So if it is discontinuous, we need to look into why. And we may need to go back to image inspection to solve that problem. Is there a missing point at any band that should be there? Here we've got a nice SED, but it stops at 2 microns. If we can see the source in the IRAC images, then we should get IRAC photometry. So this one, maybe, depending on what the images say, should go on the list of things that need additional new photometry from us. It could very well be that there's multiple sources involved, and it could very well be that there's an obvious better match to the longer wavelengths from one source. Okay, so sometimes you can see that there's 2 sources in 2-mass, but by the time you get out to WISE24, one is much brighter than the others. So when you get to WISE4, that one source should maybe get all the measured WISE4 flux, for example. But we'll have to investigate that. We have to look at the SEDs and the images together to figure that out. The SED may look highly reddened, like this one. Look, that's a really steep fall off compared to these other guys. So either that point is wrong or it's really embedded. Again, looking at the images will help us figure that out. Does the SED look like a young star SED or an extragalactic one? This one is freakishly flat. I do not know what's going on with this one. So it doesn't look anything like the other SEDs here, right? So that's an example of something where the SED shape is just weird. So another thing we're going to have to do is inspect where these sources fall in color magnitude diagrams and in color diagrams. And we're going to have to do it for each object. So remember, an SED is going to give you multiple wavelengths all at once, but for just one source. A color magnitude and color diagram is going to give you only up to 4 measurements but for many sources at once. So we can figure out whether or not the YSOs we care about are falling where they should be in any of a huge number of color and color magnitude diagrams. And we can look at IR ones to figure out if there's evidence of a large IR excess. Is there evidence of reddening? And we can look at the SED in images to help with that interpretation. And does it make sense? Does the SED shape make sense for where it's falling in the color and color magnitude diagram? Or is something wrong because probably there's a point that's wrong? So here I have just an example of a WISE color plot. And this source right here is red, really red in both WISE colors. And if you look at the SED, you see why. Yeah, it is a bright young star there. And then here we've got something that's much less substantially an outlier. It has much smaller excess. And if you go look at the SED, yep, that's consistent with that interpretation, all right. So this is not going to be cookbook science. Nothing that we're going to do here is going to be like cookbook science. So at least one of you, if not most of you, is going to be really, really frustrated with me because I am not telling you, okay, look at my screen. I'm going to share my screen. Okay, everyone click this button. Nothing we're doing is going to look anything like that. I'm going to say, make a color magnitude diagram. Here's the catalog. So it's going to be on you to figure out how you need to do that. And you're going to get help from everyone here, but everyone may be working with a different version of Excel. Certainly I've got a Mac and most of you have Windows, so there's going to be a different interface from that. So we're not all going to be doing an all click together kind of situation. There's going to be lots of independent work, and it's going to be hard because we have to do this over Zoom. And I know, and it sucks, but we're going to try to make it work. So I'm trying to map our goals with the tasks that I just described and the actual files that you can find on the box drive. So working with images and catalogs is sort of ubiquitous. It's going to underpin everything else that we do. Our main goal, number one, is we need to define the nebular stream and decide if the stars that are encompassed by that definition are likely to be young stars. So in order to do that, you're going to need to know how to work with images and catalogs. You're going to need to know how to understand some of the spatial resolution stuff that we've been talking about but haven't actually done yet this spring. We're going to need to make SEDs. We're going to need to know how to do image inspection, and we're going to need to know how to make color magnitude and color diagrams. The images and catalogs, there's 2 files that go with it. Data loading, but also define the nebular stream. So that nebula stream task has a dotted arrow because it's going straight from define nebular stream to that document specifically. Now the spatial resolution stuff has 1 file that's an adapted version of the stuff I distributed in the spring. In order to make SEDs, there's 2 files that I think you're going to find useful. The specific SEDs instructions, but then also the cheat sheet that has a list of wavelengths, 0 points, and the symbols that are used in my SEDs. There's the image inspection process, and there's 2 files that go with that. One is a general description of source inspection, like the things you need to worry about. And then there are some nitty-gritty examples. And I'm sorry, but the examples do come from last year. I just didn't have time to make new detailed examples of actual sources in our field because I haven't done the analysis in our field yet. And then for making color magnitude diagrams, there's a file specifically on that. Now our second goal is for the literature YSOs, we're going to look at the new data that we have now to decide if the sources that are in that literature list are still things that we think are likely young stars. And look, some of the tasks overlap. In order to do this, we need to know how to make SEDs, inspect images, and make color magnitude diagrams. So once you've mastered them in the context of goal 1, goal 2 should happen pretty straightforwardly. And then the stretch goal, 1A, that I'm pretty sure we're going to get to this week, is we're going to compare the previously identified clusters using color magnitude diagrams. So that depends primarily on the make CMDs part. and there's a file specifically for this task. Now, for our other goals, stretch goal 1B was look at the apparent members of clusters to try to identify members. That involves making SEDs, image inspection, and making color magnitude diagrams. Stretch goal number 2, for the long wavelength detections, decide if they're likely YSOs. Same thing. So once you've mastered those 3 things, once you get to the point where you can do them quickly, it's going to be straightforward to do these other sources. And stretch goal number 3 is a sort of a separate entity that's going to be exploring the optical variability, and I haven't developed any materials for that yet because I'm pretty sure we're not going to get to that this week. And then also sort of hovering in the background is that for sources that are missing Iraq photometry, we need to go do it. I don't have any materials developed right this second for that because I'm not sure how we're going to get to it. If there's enough interest, we'll have to organize another day to get together and go through it for those that are interested. And in any case, I can also just do it for you. That works too. On computers in general, just because the computer says it does not mean it is right. You always need to apply your brain and see if it makes sense. So the pipelines that have already generated these catalogs are pretty awesome, and they do a fabulous job overall. But they're going to struggle in regions where there's lots of stars and lots of nebula, and the region is complicated, and that's what we have. So the computer is going to try and tell you when it thinks it's struggling, be it, because it's going to give you quality flags and other things to look at. And sometimes it just doesn't know that it's struggling. And that's why we need to spend some time actually exploring SEDs and images and color magnitude diagrams. Excel is going to spit out lots of numbers, and it's going to do exactly what you asked. But did you ask it to do what you thought you did? I guarantee you that the first SED you make is not going to be right. You're going to be off by many orders of magnitude, and it's going to be fine. You just need to debug what you've told Excel. So you're going to need to take really good notes. You're going to need notes that are still going to make sense to you in October and November and December, if not even later. So write it down. Take good notes. If you would rather do it analog, have a notebook and pen next to your computer. If you'd like to do it on the computer, start a file now. So we're going to do this. You're going to experience the thrill of discovery, the incredible visceral feeling of doing something no one has ever done before, seen things no one has ever seen before, and know something that no one else has ever known. That's science. So welcome to it. Let's do it.